Today we're starting Unit 10, and the first unit is on sequences. So what is a sequence? A sequence is a function whose domain is the set of positive integers. It is common to represent sequences by subscript notation rather than by the standard function notation. So as you can see here, 1 is mapped onto A1, which is the first term, 2 to A2, and so on. Let's scroll a little bit here. So the numbers A1, A2, all the way to AN are the terms of the sequence. And when we talk about A sub n, which is right here, that's the nth term of the sequence. And if I ever talk about, or you ever see something that talks about the entire sequence, the notation for the entire sequence looks like what I just underlined. Whenever we talk about sequences, because we're going to eventually get to series, a sequence is, we kind of think of it as it's a list. Okay. And I'm going to scroll down here. I want to see if I can hide that for a minute. There we go. And back. Here we go. Okay. And so when we talk about a finite sequence, I'm going to give an example. 1, 3, 5, 7, 9. But we also may talk in terms of an infinite sequence. And we talk about an infinite sequence. That could be 1, 3, 5, 7, 9, and forever. So that's important to keep in mind. All right, let's go to the next page. And on the next page, we are going to do an example. Write the first 5 terms of the sequence. So here we go. We're going to start with n equal to 1. So therefore, the first term is going to be 3 to the first over 1 factorial, which is 3. The second term, n is 2. 3 squared over 2 factorial. Well, that's just going to be 9 over 2. And the third term, 3 to the third over 3 factorial. I probably should review with you factorial here because 3 to the third is 27. And when we talk 3 factorial, that means 3 times 2 times 1. So that's 27 over 6, which we can reduce to 9 over 2. Okay, I'm going to scroll down. And the fourth, oops, come on. And let's get my pen back. The fourth term is going to be 3 to the fourth over 4 factorial. Well, 3 to the fourth is 81. 4 factorial is 4 times 3 times 2 times 1. So that's 81 over 24, which reduces to 27 over 8. And the fifth term, 3 to the fifth over 5 factorial. So 3 to the fifth is going to be 243. 5 factorial is 5 times 4 times 3 times 2 times 1. So we have 243 over 120. That reduces to 81 over 40. Pretty basic, this first part. So when it's asking you to write the first 5 terms of the sequence, this is what you're going to do. 3, comma, 9 over 2, 9 over 2, 27 over 8, and 81 over 40. That's how you list terms of a sequence. Terms of a sequence are separated by commas. Next example. Write the first 5 terms of the sequence. So this one's pretty basic, but we'll go through it anyway. So when we have the first term, so that's 2 times 1 over 1 plus 3, that's 2 over 4, which is 1/2. And the second term, 2 times 2 over 2 plus 3, 4 over 5. And the third term, 2 times 3 over 3 plus 3, 6 over 6, which is 1. And the fourth term, 2 times 4 over 4 plus 3 is going to be 8 over 7. And the fifth term, 2 times 5 over 5 plus 3, that's 10 over 8. And extend my page, and that reduces to 5 over 4. So here we go. 1/2, 4/5, 1, 8 over 7, and 5 over 4. Again, pretty basic, right? The first 5 terms of the sequence, it's a list. Next page. Okay, so example 3. Let's start all again. So when n is equal to 1, so we have the first term, -1 to the 1 plus 1, 2 over 1. So let's go back to review PEMDAS with you. -1, that's -1 squared, which is a positive. So the first term is 2. The second term would be -1 to the 2 plus 1, 2 over 2. Well, 2 plus 1 is 3. -1 to the third is negative, so that's -1. And the third term, -1 to the 3 plus 1 times 2 over 3 is going to be 2 over 3, because that's going to be -1 to the fourth power. And the fourth term, -1 to the 4 plus 1 times 2 over 4 is going to be -1/2. And I'm going to put the fifth term up here, -1 to the 5 plus 1, 2 over 5. So that is going to be, this is going to be a positive, so it's going to be 2 over 5. So again, when we write our list of the first 5 terms, here we go. 2, -1, 2/3, -1/2, and 2/5. And that's exactly what we found up here. All right, so this is now this is a little bit different. This is talking about writing the first 5 terms of a recursively defined sequence. This can be a little more difficult. So they give us the first term is 4. Every other term is based on this recursive formula. So if we're trying to find the second term, that means k has to be 1, because 1 plus 1 is 2. So if k is 1, I'm going to plug k in, 1 plus 1 over 2 times, so this is why it's recursive. Each future term is based on the term before it. So 1 plus 1 is 2 over 2 times the prior term, so we get 4. So now the third term is going to be 2 plus 1 over 2, and now we're going to use the second term. So we have 2 plus 1, so that's 3 over 2 times 4. That's 12 over 2, which is 6. And I'm going to keep going. When k is equal to 3, that's finding the fourth term. So we have 3 plus 1 over 2 times the third term. And so we get 4 over 2 times 6. That's just 12. And let's keep going. I think this is our last term. Yep. So we have 4 plus 1 over 2, and we use the prior term. That's 5 over 2, times 12. That's going to be 30. So here are our first 5 terms of our recursively defined sequence. They are 4, 4, 6, 12, and 30. 4, 6, 12, and 30. Yep. So all of these before, each term was independent of the prior term. Now, when you talk recursive, each new term is based on the term right before it. Still is a list. Those are sequences. Okay. Let's talk about the definition of the limit of a sequence. Limit is never going to go away. Let L be a real number. The limit of a sequence, remember, let's go back to the first screen here. The entire sequence, there's the terminology, how we write it when we're talking about an entire sequence. So the limit of a sequence, A sub n, the entire sequence, is L. written as this notation right here. So let's talk about the limit of a sequence. Let L be a real number, let F be a function of a real variable such that, and they give us this limit notation, if A sub n is a sequence such that f of n equals A sub n, that's the final term of the sequence for every positive integer n, then the limit as n approaches infinity for that sequence is going to equal L. It's going to approach some value. So when we're talking about sequence, remember a sequence is a list. So if we're taking the limit as x or n approaches infinity, we're finding the final term, not a sum, the final term of the sequence. Okay, here we go. Example 5. Find the limit, if possible, because it's not always possible, you will find that. So here we go. The limit as n approaches infinity of 5 minus 1 over n squared. Okay, so the limit as n approaches infinity. Well, we can see this right here. The limit of a constant is the constant. As n approaches infinity, this denominator is getting bigger and bigger and bigger, so this is going to approach 0, so the limit is equal to 5. I'm assuming you all hear my dog, but I'm trying to, hopefully the dog can be quiet. So here we go. Determine the convergence or divergence of the sequence with the given nth term. So let's go back here. There's the given nth term. We found the limit. If the sequence converges, find its limit. So let's talk about, I think we've covered a while back convergence, divergence. Convergence means a limit exists. Divergence means a limit does not exist. So that's why it says, if the limit converges, find its limit. So what I like to do, the last one was pretty quick and easy to find a limit. I didn't need to do much work, but look at it and see, yeah, it's the limit, so the final term of this sequence is going to approach 5. On this one, it's a little more difficult. So what I like to do when I'm finding the limit of a sequence, I like to start by testing out some terms. So the first term, if I plug in 1, I'm going to get 0.5. If I find the second term, that's 0.56. If I find the third term, that's 0.59. If I find the fourth term, that's 0.79. Nope, not the fourth term. That's not what I meant. I meant the 50th term is what I meant. The 50th term is going to approach 0.79, and I even tried the 1,000th term, 0.91. Looking at this whole progression here, I'm going to say the limit is probably going to equal 1 based on, let me fix this right here. Based on what we're seeing right here, I'm thinking it's going to approach 1, but we can't just assume that. Now we're going to go over here and we're going to take a limit. So if we take the limit as n approaches infinity of this sequence, as I can see, I'm probably going to get infinity over infinity. Okay. So we know that's going to be L'Hopital's, and recall way back when in Unit 3-4 when we did L'Hopital's, we want to look at the limit of the top. That's going to equal infinity. We want to look at the limit of the denominator. That's also going to equal infinity. So therefore, we can say by, all right, come on. My pen sometimes goes crazy on me, so just bear with me here. Scroll down. We need more space. There we go. Oh, okay, let's get my pen back. By L'Hopital's, here we go. The limit as n approaches infinity is going to equal the limit. Take a derivative of the top, which is 1/3 n to the negative 2/3, and of the bottom is also 1/3 n to the negative 2/3 because in case you're confused, this is written as n to the 1/3. Take a derivative, the 1/3 goes in front, we subtract 1 from that. Oh, well, the numerator and the denominator equal each other. So look at that. And the limit as n approaches infinity of a constant is the constant. And we thought, based on looking at the terms of the sequence, it's going to approach 1. And yes, it sure did. And so this is definitely considered a converge for sure. And it says, then find its limit. That means that, think about what this means. As I keep picking numbers, bigger and bigger and bigger n values, what it's going to happen is it's going to eventually just get very, very, very close to 1. That means the final term of this sequence is going to approach 1. Not the sum, the term. Next page. All right, example 7. Determine the convergence or divergence of the sequence with the given nth term. If the sequence converges, find its limit. I'm going to do the same thing I did in the last one. The first term, what will that be? Well, 1 plus -1 to the first power, well, that's 0. The second term will be 1 plus 1, because -1 squared is 1, so that's 2. Oh, the third term, 0. The fourth term, 2. The fifth term, 0. The sixth term, 2. Oh, what is happening here? What's happening is it's going back and forth between 0 and 2. This will never converge onto a single value, which says that the limit as n approaches infinity of 1 plus -1 to the n does not exist, which is called a diverge. That's all you have to do. That's why I always start by trying different terms, because that helps with understanding what the actual limit will be. Example 8. All right, on example 8, here we go. I'm going to do the same thing where the directions are exactly the same as the example we just did. So the first term is going to be 1 plus -1 to 1 over 1 squared. That's just 0. Second term is going to be 2 over 4. That's 1/2. The third term, let's see, 1 plus -1 to the third over 9. Oh, that's going to be 0 again. The fourth term is going to be 1 plus -1 to the fourth over 16. That's going to be 2 over 16, which is 1/8. But I'm going to look at these as decimals, which will help me see. So this is like 0.5. So look at this. So the fifth term, again, is going to be 0. The sixth term, if we plug that in, is 0.056. I then went and tried the 50th term, 0.0008. Okay, I'm guessing that the limit is going to approach 0. But different things are happening, whether it's an odd or an even integer. So we have to create a statement that looks like this. So I think we can state that the limit as n approaches infinity of 1 plus -1 to the n over n squared is going to equal 0, and that's a converge. But let's make sure you understand, because here's what's happening. This is going to happen a lot on different sequences. For odd integers, look what's happening. For odd, the limit as n approaches infinity is always, for odd, it's always going to be 0 over n squared, which is 0. For even integers, notice, it's always going to be 2 over n squared. 2 over n squared. So it's always going to be 2 over n squared, which is also 0. So yes, that limit is going to approach 0, and we can tell by listing out the different terms of the sequence. Example 9, same thing. Here we go. On example 9, we have the first term. If you plug in 1, that's 0. I'm just going to do this kind of quick. I'm going to write what I found when I did this ahead of time. And the fourth term, 0.173. And the fifth term, 0.161. And then I jumped down to the 50th term, and I got 0.039. And I even jumped to the... Oh, come on. Bear with me. There we go. Crazy. It's called my crazy pen. Then we go, I lost my spot, to the 200th term, 0.0132. Well, if you look at this, you know, it's kind of going up, going down, going up, then going down, and it's continuing to go down. I'm thinking if we kept trying different terms, I think this is going to approach 0. So let's take a look. The limit as n approaches infinity. Oh, look at this. I'm not even going to write this out because we can see right away that we're going to have infinity over infinity. So I'm going to take the limit of the top. I'm going to take the limit of the denominator, the bottom, and then I can state by L'Hopital's. Sorry, my handwriting gets kind of messy on this board that I'm using. By L'Hopital's. Here we go. We're finding the limit as n approaches infinity. Oh, that does not look good. Try that again. As n approaches infinity of... Okay, so we can rewrite this as 1/2 ln of n over... Okay, let's try that again. 1/2 ln of n over n, because ln of the root n, that's n to the 1/2. That's a natural log property. So now I'm ready to take a derivative of the top. The first step was just to rewrite. So the derivative of ln of n is just, it'd be the derivative of n over n. Well, the derivative of n is 1. So that would be 1 over, there's that 2n over 1. And now, oh my goodness, I'm not doing good writing my infinity. Okay, so that's really looks like that. Well, as n approaches infinity, guess what? A converge, and I don't know what just happened just now. So let's go back. Did I lose my whole page? Let's just back. Here we go. Yes, I did lose my whole page. That is a converge. There's the limit, and that is a converge, just like we thought. All right, here we go. Determine the convergence or divergence of the sequence, same directions, and this is kind of a special one. When you plug in 1, I'm going to do this quickly. Plug in 3. I want to use the 4th term, which is that. I did the 5th term. I did the 6th term. And I jumped to the 49th term. It should be a negative. And I even did the 50th term. I think the limit's going to be 0 again, based on what I'm looking at here. But different things are happening whether the integer is odd or even. So let's talk about this. When we're talking about odd integers, take the limit as n approaches infinity. Odd integers, anytime you get an odd integer, you're having -1 is in the top over n squared. It's -1 over n squared. Well, that limit is 0. And when we take and talk about the even integers, that's the limit as n approaches infinity of, well, the even, it's a positive 1 over n squared. Well, that's also going to approach 0. So therefore, based on that, when you're looking at the odd and the even, both of the limits approach 0. So we can make the statement that the limit as n approaches infinity of cosine of pi n over n squared equals 0. And that's definitely converges. All right. I want to just quickly refresh your memory on factorial, which we kind of did at the beginning of the lesson. And so when we talk about factorial, you write the current number times the number 1 less than it all the way down to 1. And 0 factorial is equal to 1. So when we write it, n factorial is really going to be n times n minus 1, n minus 2, n minus 3, and end at 1. So let's do this example 11 right here. N plus 2 factorial, you start with whatever's being factorialed, and that's n plus 2. 1 less than n plus 2 is n plus 1. And I'm going to stop there. Why? Because the denominator has an n factorial, and they are going to cancel, and we get n plus 2 times n plus 1. This is going to come into play when we start talking about series and series tests. All right, that is it for today. So I'm hoping that you understand the video, and I'll see you tomorrow.